Okay, let's look at this problem, balanced binary tree. Given a binary tree, we need to determine whether this tree is balanced or not. The height is balanced or not. So a tree is balanced if the height difference isn't greater than 1. So for this one, the difference is just 1 in height difference. For this one, it is 2. Therefore, this one return false. Okay, so yeah, to solve this problem, what you can do is use a bottom-up approach. So essentially, you go to the leaf, and then you start moving upward. And as you move upward, you want to calculate the height of each subtree. And you also want to check whether the tree is balanced or not. So if it isn't, then you want to propagate that state upward so that when you are checking for other nodes, you also just already know that it is not balanced, and you really just don't need to do any further calculation as well. So let's go ahead and code up this solution then. Okay, so let's do our depth first search on the root of the node. Then we can return the height. Okay. So the first thing we want to check is whether we have a root or not for our base case. Otherwise, we can just return 0 after height if we don't have a root. And now we want to go all the way to the left to get the height of the left subtree. Left, and we also want the right. Okay, and if at any case the left hand side height is -1 or the right hand side height equals to -1, we can simply return -1. Otherwise, we take the maximum height between the left hand side and right hand side, and we can increment the height by 1. Okay. Oh, and of course we need to check that the absolute value, the height difference, is no bigger than 1. Otherwise, we also want to just return -1, indicating that this height is unbalanced. Greater than 1, just return -1. Let's return DFS height. Make sure that it does not equal to -1, because if it doesn't equal to -1, then we have a balanced tree, essentially. That's what we're checking for. And yeah, so there you have it. Oh, the space complexity is, let's see, just the call stack. So we see the height of the tree, and the time complexity is linear because we just visit each node on the tree once.